going to begin notes for section 6.3, looking at arcs and angles and how to find the measures of one or the other. So if you look in your book, there's 5 investigations in this section, and the first one is relating the inscribed angle to the arc that it intersects. So just a reminder from our previous section, this angle that I'm tracing here is an inscribed angle, and it intercepts this arc. In other words, it cuts that arc off. So we're going to take a protractor here and use the protractor to do this investigation. One of the things that you need to know in order to do this investigation is to remember how to figure out the measure of an arc. So this arc has a measure that is equal in degrees to the central angle, which in this picture would be angle O, meaning that O would be the center of the circle. So if I took my protractor and measured angle O, I would just have to line my protractor up and I'm going to measure angle O. So if we look at this protractor here, you can see that I'm going to use this dynamic angle here, and then it should give me my measure. And so if you look at it, maybe I can't, it might even be a little bit closer to 77 degrees, because I think I didn't have it quite in the right place the first time. So 76 is what it's saying there. Okay, so that, when I move that protractor, just so you can see what I'm looking at, this angle here is 76 degrees, which means this arc in red is 76 degrees. Because from the previous unit, the central angle arc measure, the central angle is the same measure as the intersected arc. So now we're going to look at the inscribed angle. So now we're going to look down here at this inscribed angle and move the protractor to measure the inscribed angle. And see what we get here. And we get 38 degrees. So let's get rid of this protractor and look at the relationship between 38 and 76 degrees. So if you haven't seen the mathematical relationship, let me see if I can get you to see it visually. Since 38 times 2 makes 76, these piece together perfectly. So the inscribed angle here is equal to 1/2 its intersected arc. In other words, if you have to find an inscribed angle in a circle, you just need to either know the central angle or the intersected arc. So that conjecture is the measure of an inscribed angle in a circle is equal to 1/2 the measure of its intersected arc. So inscribed angles intercepting the same arc must have a certain property. So first, just let's practice the other property. If I were to change this and say, let's suppose this was 80 degrees, then this this arc would also be 80 degrees, and this angle would be 40 degrees. Because if I label my picture angle ABC has a measure that is equal to 1/2 the measure of angle AOC, where O is the center of the circle. So if I drew another angle here, just think about the first conjecture. I can draw lots of inscribed angles that intercept arc BC. So because if I made this X, I'd have just a different inscribed angle, measure of angle. Oh, look, this is a mistake. This should be angle BAC. And this should be angle BOC. Sorry about that. Now, measure BXC would be equal to 1/2 of the measure of BOC, because BXC also intercepts this arc. Therefore, these two angles have to be the same. The measure of angle BAC has to be the same as the measure of angle BXC, because they intercept the same arc. So they're both 40 degrees. So no matter where I draw the angle, even if it's over here, each time I draw an angle, if it intersects the same arc, they're going to have the same measure. Okay, let's look at the third one. Investigation 3, inscribed angles. Inscribed angles in a semicircle. What would that look like? So if I take an angle and I make it inscribed in a semicircle, it would have to have its endpoints on the diameter and its vertex on the circle. So I could draw several different angles, like this one to begin with. The intercepted arc of that angle is the one that I'm scribbling over here. So that's a semicircle. That intercepted arc is 180 degrees. That would make this a right angle, because the inscribed angle from the previous page always has a measure of 1/2 the intercepted arc. So no matter where I draw my inscribed angle, as long as its endpoints are on the diameter, I'm always going to have a right angle. These are always right angles. And you can see my picture, a little bit of error there. It looks, whoops, maybe didn't land exactly on the endpoint there. So angles inscribed in a semicircle are right angles. Okay, let's look at this fourth conjecture. So we have to understand what a cyclic quadrilateral is to do this conjecture. So I'm going to take a circle and draw a picture of it. that's a circle, and I'm just going to group it with its center so I don't lose it. A cyclic quadrilateral is a quadrilateral with all 4 vertices on the circle. Doesn't have to be regular, could be, but it doesn't have to be. So that would be a cyclic quadrilateral right here. And the thing that we want to think about is, what do we know about the measures of the 4 angles? So angle W, if you look at angle W, it intercepts this entire arc. And angle Y, so angle W, looking at angle W, it intercepts the yellow arc. Angle Y intercepts this pink arc. And if you're not sure where I'm getting that, just trace the sides of angle Y, and they cut off the pink arc. And if you trace the sides of angle W, they cut off the yellow arc. So since the yellow arc which we will label QA, and the pink arc looks to be a major arc, so we will label that QDA. Together, the measure of QA plus the measure of QDA, they make a whole circle, so they have to be equal to 360. So what does that say about angle Y plus angle W? Hopefully you guys figured that out. They would have to add to 180. Because angle Y is equal to half of the measure of QDA, and angle W is equal to half the measure of angle QA. So if I add these together, I get Y plus W is equal to 1/2 of the measure of QDA plus the measure 1/2 the measure of QA. So if we take out that 1/2, you have QDA plus QA. So that's half of 360, which is 180. So the opposite angles in a cyclic quadrilateral always have to equal 180 because their intercepting arcs always cover the circle. So if I erase this highlighting or take away the highlighting, the same thing's going to be true for X and Z. If you look at X, The intercepted arc for X is in yellow. And if you look at Z, the intercepted arc for Z is in green. So since the yellow and the green complete a whole circle, we know that X plus Z has to be equal to 180. So X plus Z is equal to 180. And we also know W plus Y equals 180. So X plus Y plus Z plus W have to equal 360. So there's two things that are true here. Opposite angles of a cyclic quadrilateral are supplementary. And all four angles of the cyclic quadrilateral sum to 360. All right, so that's our conjecture right here. Okay, last thing, and we'll practice these things in class tomorrow if you have questions. This is much easier. If I just take our another circle, I can get this circle here. The last conjecture is really very simple. So we're interested in the arcs that are formed by parallel lines. So for example, if I just drew a line, probably the easiest way to visualize this is to take a straight edge, which is way up here, and just chop off a part of the circle and get a pair of parallel lines. What we're going to find is that you probably would just use your intuition to guess that this is congruent to that. But if we have parallel lines, we can actually prove that by putting in a transversal, or just kind of talk about why that's true. Since these lines are parallel, the alternate interior angles are congruent, and since the alternate interior angles are congruent, if this has a measure of x, this would be 2x, because remember, an inscribed angle is half its intercepted arc. So in other words, putting numbers to that might make this easier for you. If this were, say, 30 degrees, this would be 60 degrees. But since the lines are parallel, this would also be 30 degrees. So this over here would be 60 degrees. So the intercepted arcs are congruent. So parallel lines chop off two intercepted arcs, and that is this pair of parallel lines, that's an in-state curve, cuts off this arc and this arc. Those are the intercepted arcs of the parallel lines, and they're congruent. All right. That's section 6.3. We'll practice in class tomorrow.